Now that we have seen the stability of implicit, explicit and Crank-Nicolson, we will going to check the ADI scheme, and this is where we'll close our discussion on unsteady diffusion. In ADI scheme, as you know, that we have a two-step procedure. In first step, we go from uij n to uij n plus half, and in then second step we go from uij n plus half to u n plus 1. So here the basic difference is as compared to our analysis of the previous schemes is that we have growth factor in both two steps. This is my step 1, this is my step 2, and we have growth factor G1 here, we have growth factor G2 here, and overall we will have the growth factor G will be equal to G1, G2. So that is how we'll take. So we have the same expression of round of aders, which we take one mode of it, the mth mode, that is given by this am exponential in time and exponential with root over -1 in space, which means periodic in space, exponential in time, and then I can go I plus minus 1, which will go in x I plus minus 1. I can go j plus minus 1, which will go in y j plus minus 1. And we know the distance between xi plus 1 to xi is delta x, xi minus 1 to xi is minus delta x, etc. The same applies to y as well, where we can go in j plus minus 1 minus yj is equal to delta y. So the growth factor, overall growth factor is capital G, which is a product of G1 and G2. And this overall growth factor is epsilon ij n plus 1 divided by epsilon ij n. And G1 is the first part, epsilon ij n to epsilon ij n plus half. And G2 is the second part, that goes from n plus half to n plus 1. Now, with this basic idea, we can check it out that epsilon I plus minus 1 by epsilon I j n, it will give us exponential plus minus p km delta x, and which is the exponential plus minus p beta, where we are taking this km delta x as beta as always. And thus, if instead of n we go up to n plus half, that will give us ij n plus half divided by ij n, that is part 1, and that will give us the G1. In the second part, in n plus half, we go from I to I plus minus 1, so that will give us exponential plus minus p beta. So overall it comes as G1 exponential plus minus p beta. Similarly, as I go from n plus 1, n plus half to n plus 1, it will give me G2 exponential plus minus p beta. In the same manner, when I go from j to j plus minus 1, if both are at time step n, then it gives us exponential plus minus p theta. But when I go from epsilon ij as n to epsilon ij n plus half, I have G1 multiplied by exponential plus minus p theta. And in same way, when I go from n plus half to n plus 1 with j to j plus minus 1, I have G2 multiplied by exponential plus minus p theta. With this idea in mind, we'll now take up the step 1 of our ADI algorithm. In step 1, I go from n to n plus half, and the del 2 u del x2 is discretized at n plus half. The del 2 y del y2 term is discretized as n, so that we can use this triagonal solver. And we already know that g1, how that is related to g1 exponential plus minus p beta, how that is related to ratio of this epsilons. So now we can have this equation of round of error. I take that mode here, error mode, I put it in place of u, and then I divide both sides by epsilon ij n. So in left side I get g1 minus 1 divided by alpha delta by 2, and in right side I have this epsilon ij and I minus 1j n to n plus half. Here I plus 1 n plus half and I n. This goes the first term, which is n plus half times time step, and here is the second term. In second term I have everything as n, so epsilon ij n, epsilon ij minus 1 n, epsilon ij n, epsilon ij plus 1 n here. So I can write this as twice g1 cos beta minus twice g1, because this is exponential p beta minus exponential minus p beta, and that gives us twice cos beta. Similarly, the second term I have twice cos beta. I do not have any g here because everything is at nth time step in the second term. So I can write now using this rx equals alpha delta t by delta y square and ry is alpha delta t by delta y square. I can write this g1 minus 1 equal to rx g1 cos beta minus 1 plus ry cos theta minus 1. Overall, it will give us an expression of g1, that is 1 minus ry, 1 minus cos beta divided by 1 plus rx, 1 minus cos beta. Now we come to step 2. And in step 2, I have this n plus 1 to n plus half to n plus 1, this jump. And here the first term del 2 u del x2 is discretized at n plus half, del 2 y del y2 is discretized at n plus 1. So if I now write the equation of round of error, I get in left side g2 minus 1 by alpha delta t by 2, and this will take us twice cos beta minus 2 by delta x squared, because everything here at n plus half time step, so g doesn't appear here. But then the second term del 2 u del y2, here g appears because I have epsilon n plus 1 divided by epsilon n plus half in both the terms. So I have twice cos beta minus 2 by delta x squared, twice g2 cos theta minus twice g2 delta y square. So what I have is this g2 minus 1 is rx cos beta minus 1 plus ry g to cos theta minus 1, where this rx and ry are the same expression, alpha delta t by delta y square, alpha delta t delta x square. So at the end I get this expression for g2, that is 1 minus rx into 1 minus cos beta, 1 plus ry, 1 minus cos theta. We are now ready to apply g equal to g1, g2. We received both the expressions of g1 and g2. So let's see how it turns out. So I have g1 is 1 minus r1, 1 minus cos theta, 1 by rx, 1 minus cos beta. g2 is 1 minus rx, 1 minus cos beta divided by 1 plus ry, 1 minus cos theta. So when I multiply, I get this two terms here multiplied, and I can arrange them. I take this beta together and theta together. So I have the first term is 1 minus rx, 1 minus cos beta divided by 1 plus rx, 1 minus cos beta. Second term is 1 minus ry, 1 minus cos theta, 1 plus ry, 1 minus cos theta. So I have 1 minus 2 rx sine square beta by 2 divided by 1 plus 2 rx sine square beta by 2. Similarly, here I have ry sine square theta by 2. Now you can see that I can write this expression as 1 minus c1 divided by 1 plus c1, 1 minus c2 divided by 1 plus c2. c1 is twice rx sine square beta by 2, which is of course greater than or equal to 0. Similarly, c2 is twice ry sine square beta by 2, that is also greater than or equal to 0. Since both c1 and c2 are greater than 0, we can write that 1 minus c1 modulus of that is less than or equal to the absolute value of 1 plus c1. Similarly, 1 minus c2 and modulus of that equal to less than or equal to modulus of 1 plus c2. So overall, if we see now, the absolute value of g will be absolute value of 1 minus c1 multiplied by 1 minus c2 divided by absolute of 1 plus c1 into absolute of 1 plus c2, and this must be less than 1. Thus, we can clearly see that the ADI is unconditionally stable. So we have now completed our discussion on explicit, implicit, Crank-Nicolson and ADI, all the schemes. We know how to apply all these schemes for unsteady diffusion problem. We have also seen the stability characteristics of all these schemes. You can now think about that in which case which scheme should be applicable more. So you can write down the relative advantages and disadvantages of all these schemes and think about their applicability. That's all for this lecture. Thank you, and I'll see you in class.